Hello friends, so today we are solving this problem, minimum score after removal on a tree. So there is an undirected tree with n nodes leveled from 0 to n minus 1 and n minus 1 ages is given to us. So we are given a 0 index integer array nums of length n, where nums I represents the value of ith node, and we are also given a 2D integer array edge, like the details of ith edge from ai to bi, right? So you can visualize like this. So suppose this is our tree, then we are given this nums. This nums has the values of every node. For example, these values are the index of the node, right? And these red colored values are the actual value. For example, here, see, you can visualize here, 0th node have the value 1. Second node has the value 5. Similarly, node 2 equal to having the value 5. Node 3 has the value 4. Node 4 has 11, right? So like this. So these are the in nums has the value of those nodes, and 0, 1, 2, 3 like that. These are the index of the nodes. We are also given the age, right? Like we have a 0 to 1 we have an age, 1 to 2 we have age, 1 to 3 we have age, 3 to 4 we have age. So we are given like this. Now what we have to do is remove two distinct edges of the tree to form a tree connected components. For a pair of removed edges, the following steps are defined. So basically we have to remove two edges there. So get the XOR of all the values of the nodes for each of these three components respectively. So if we break the tree with the two edges, there would be three different trees, right? So for those three different trees, we have to do the XOR of all the values that are given in the nums. Okay. The difference between the largest XOR value and the smallest XOR value is the score of the pair. So what we can do here is, for example, let's say we are deleting this edge. Suppose I am deleting this edge, right? So we will remove this edge. We remove this edge, and we have to remove one more edge. Let's say I am removing this edge, right? So we will remove this edge. Now we have three different components. So these are 3 and 4. These are 1 and 5. And this value has 5. So whatever is there in nums. So what if we do the XOR of all these guys? Let's say we are doing the XOR one. So I'm calling x1 for the first. So what would be the XOR of this? 11 and 4. So we have to get the XOR of 11 and 4. What would be the value here? Value would be 15. You can do the XOR. It's a very simple, right? Similarly, we have to go for this guy. We have this is one more component we have. So for this component we have 1 and 5. So what would be the XOR of 1 and 5, right? So we have to find that XOR. So let's say we are taking one XOR example itself. So 5 would be like this, 1 0 1, and this would be 0 0 0 1, right? 0 0 0 1. So if we go to the XOR of it, whoever is opposite, so they are same, 1 and 1 same, so we will get 0. 0 and 0 is also same, so we will get 0. But here 0 and 1 is opposite, so we will get 1. And 0 0 same, so we will get this. So we got 4 here, right? So XOR of this guy we got 4 here. Now we'll do what will be the XOR of this third component. This is 5 only, right? Because no one is competing with it. So 5. So we have got 3 XOR after removal of the 2 of the edges. So we got 4, we got 15, 4 and 5. So what would be the maximum difference? So maximum is 15 and minimum is 4. So if we do 15 minus 4, this is giving us the answer equal to 11, right? But this is giving for this particular removal. But we have to do such removal so that this difference comes least, right? This difference would be least. So let's say we are doing another removal. We will remove all this. We will bring back to the original position. Now this time, let's say we are removing, let's say we are removing this guy. Okay, I'm removing this, and let's say I am removing, let's say I'm removing this guy also. Okay, so what will happen here? 11, 4. So we have to make all the XORs, right? So let's say we will make XOR 1 of x1. So what would be the values here? 11, 4 and 5. We have to do the XOR of all these guys. 11 and 4 and XOR of 5, right? So we are using the XOR of all these guys. So what would be the answer? We got 11 and 4. We got 15 and 5. So it would come 10. You can do. XOR is very simple. Now we'll go to x2. What is the XOR of x2? So x2 has only one value, that is 1, so it would be 1 only. What is the x3? So x3 has the component 2 only, right, which value has 5, so its answer would be 5 only. Now you have to find what is the max here. Max is 10 and minimum here is 1, so 10 minus 1, so this time we are getting 9. We are getting 9, so it's bigger than the previous value. So there could be multiple such removals when we have to find the maximum value of XOR component and the minimum value and difference of them. So whoever is minimum, that should be our answer, right? So in this case, like 9 would be answer. So this is what we have to do. Now the next thing is how to do that. That is the important thing. So guys, before jumping to the solution, we want to build the intuition. We just not going to solutions you can find anywhere, right? So we have to find what would be the intuition behind this. So you can observe one thing here. Okay, consider this is a graph in general, because tree is also a kind of graph only. So whenever we do a BFS or let's say DFS, okay, so whenever we do a DFS immediately called its child, right? On whatever node we are calling it, it goes immediately for another child of it, then that guy also. So for example, let's say our DFS is being called here at node number 4, right? So once we are reaching at this 4, suppose we are taking the in time, let's say in time was 1, okay, so when DFS was called at 4 node, its in time was 1, it entered at 4, and as soon as it entered at 4, it will call this adjacency thing, right? And in the adjacency it will one by one call, so it will call, let's say 5, right? So when it will call 5, at that time in time of 5 would be 2, right? So in time of this guy is 1, then in time of this 5 would be, let's say in time of this 4 is 1 when we call the DFS. In time of 5 would be 2, right? Then 5 would be calling to those guys who are connected to this guy. So in time of 6 would be 3, right? Then 6 would be calling this guy. So in time of 7 would be 4, right? And when we are done till here, we are coming back to this guy again 4. Right, from where we started. So at the time when we were coming out of this 4, the time would have become 5 if we are taking the unit time. So clearly say that when on this node number 4 we called the DFS, in time was 1, and when we visited all these guys subsequently, when call came back to this 4, the out time was 5, right? So now one thing you would have observed, that if this is an ancestor, right, this 4 is an ancestor, then all the subsequent child would have a higher in time, but out time would be smaller. You can see when 7 occurred, the in time was 4 and out time was also being 4, right? So we can generally say that when DFS was called on this 4, it entered at 1 and the out time was 5. So all those guys who are below it has the in time would be always greater than this 4, and the out time would be always the smaller than this 4, because it goes like this, right? It goes like this, then it goes like this, and then out time would be coming back, right? We go back, right? We go back like this. So out time would be always would be the higher for the one where we called it, and in time would be always smaller. So with this assumptions, we can write our algorithm. So where this assumption is coming, what does it mean? If we have cleared for this in time and out time concept, we are fine. So now we are also fine with this assumption. If you observe that on any parent, when we are calling, so at any x node, now we can clearly say that, let's say u and v are the two nodes of a graph, and if we have called a DFS on these u and v, so if the in time of u, okay, if in time of u is smaller than the in time of v, then we can directly say that u would be the ancestor of v. Also, if the out time of u is greater than the in time of v, then also we can definitely say that u is the ancestor. So if these two condition matches, we can directly say that u is the ancestor of v. Okay, So with this condition, u is ancestor of, we can say u is the ancestor of v. Now what does it mean where we are using this thing? So we will write one DFS method which will park all these in time value and out time value. Okay, so we will use that information to solve this problem. I'll tell you how. So let me show you code. So see here what we are doing. First of all, anyway, we are just creating one adjacency list because we are just given the ages, right? So we are creating the adjacency list, which is list of list, and then we are adding, right? Here we are adding because this is an undirected tree. So for that reason we are adding both of them, 0 to 1 and 1 to 0, right? Both nodes should be connected to each other from both sides. Now what we are doing here is at the line number 14 till 17, we have created the array XOR-val, in time, out time, right? So XOR-val would be basically having the XOR values of every node when we call the DFS, and in time is the when DFS called first time, and out time is the when DFS returned to the parent. Okay, so we are creating these values, and this guy sitting on 17, this is a single variable kind of int count, but I am writing the code in Java. For that reason I have created this as an array of length 0, right? Because Java is pass by value, so for that reason I am taking so that it wouldn't lose the value. Util method here, you can see here. So we are calling this DFS util method on node. Okay, this is node is like any node of that tree where we are starting it, and this is the parent. So initially we will call it on 0 and parent would be -1. Okay, so you can see here we are passing that nums, the nums which is given in the question, and then we are passing the adjacency list of it. And now you can see here these are the three array which will be calculating the XOR value of node or all the nodes, and the in time and out time of the all the nodes, and this is count. So because I am using Java here, so this count is basically an array of size 1. Why I am not taking directly only int count? Because Java is pass by value, so for that reason I am passing it as a array of size 1. If you are doing this in the C or C++, you can directly write int count. This is just to keep the count that we were doing here, right? So for example, if DFS is being called at this location, in that case what will happen? Our in time, let's say it appeared at 4 at in time 4, at in time 1, that at in time 2 it would call 5, at in time 3 it would call 6, at in time 4 it would call 4, right? So this counter can keep these values. So counter, initially this counter has value 1 when it came to 4, then it came to 5, so initially it has the value 1, then it came to node number 5, it become 2, then it called to node number 6, then it became 3, at node number 7 it became 4, and when we are after completing DFS till 4, it is coming back to control would come back to the node calling node 4. So at that time it would be out time. So the in time of 4, 5, 6, 7 would be 1, 2, 3, 4, and out time at 4, the time at which DFS came back to the 4, it was 4 only, right? So this is what we will go do in this DFS. So see here, as soon as we are calling it, we are increasing this in time equal to count 0 plus plus. So count would become 1 now. So in time would be 1, and XOR values initially we have to go with node, whatever node value has. Then we are calling the adjacency list of this node, right? So if it is child equal to parent, then we cannot call, right? We cannot go back to our parent. So then we are calling immediately this DFS on the child, and now parent become node, right? And we are calling everything. Now see here we are doing the XOR val. XOR val node equal to whatever is the XOR of this node into the XOR of this child, right? So now you guys can think recursively that when we are calling this DFS, it would be calculating the XOR value of this child, and same for its child. So anyway, when we will come out at line number 74, we would have already calculated XOR value for child. Then we are making the XOR value calculated with the current node. Okay, and also we are making the out time equal to count 0. So initially we increase it by 1, right? When same thing would have been called at here at line number 17.3, then count would have been increased every time. So when we will come out of out time, it would be like the way which we were doing here, out time became 4, right? So in that way we are calling here. So this DFS util method is doing nothing, but it is calculating the XOR and out time and in time of everything or on whatever node we are calling it. So this DFS util method we will using to solve our problem. You guys can observe here, initially I am calling since line from 14 till 17, I am calling creating the XOR value in time out time of size n, and this count is of size 1 variable, which is an in form of array I am taking. Now we are calling this DFS util. So we are calling out node 0 and parent of it is -1 and all these values. Now you guys can see here, this is the result value. Initially I am putting the max value because we are returning the minimum value. Now see here, I am starting for all the nodes u and v, right? We can consider u and v. So for that u and v, what we are doing here is we are starting from 1 till n-1 and we are taking the u plus 1. So basically we are choosing any u, then we have, this is the range to choose another node, right? So see here, if the in time of v is greater than the in time of u and in time of v is lesser than out time of u, so in that case what will happen, we can clearly say that u would be the ancestor of v, just like here we were doing. See, in time of 4 was 1 and in time of all other guys were greater than 1, but out time was greater than the all these guys, right? So we can see here that in time of u, see here, that if in time of v is greater than in time of u, this is the one condition, and the out time of u is greater than the in time of v, then we can directly say that u would be the ancestor of v, right? So if we came to know if this condition, that means u is the ancestor. So if u is the ancestor, then what we are doing? We are getting the XOR value. So you can see XOR value of 0. So XOR value of 0 means everyone who is below 0, we got the XOR of all of them. Okay, it would be look like that if we do the XOR of 0, this would be the XOR value of 0 would be equal to XOR of all these guys, whoever is the node below it. This would be the XOR of all of them, right? Now we are doing then XOR val of u. So why we are doing this? So at u, if let's say we are breaking the point, right? So consider this is our u. So if this is our u, if we are breaking it like this, let's say we break like this, then if we have to calculate the XOR of this portion. So XOR of this portion, if we have already calculated the XOR of everything that is sitting at this location, XOR u, okay, and if we are breaking it here, let's say I am breaking, so suppose I am breaking it like this, this is a condition where I am breaking, so suppose I am breaking here, okay, fine. So at XOR u, you can see here, at XOR value 0, we have the XOR of all the values below it, and then we are making XOR val of u, right? Why we are doing this? Because all of them we already calculated, right? At 0 we have the XOR of all of them. Now if we want to get the XOR of only this portion where we have made the cut, how we can find that? We can find that if we get the XOR of all the nodes and then do the XOR of this portion which is sitting at XOR u, then we will find this. Now some of you might have questioned that how I can say this, because see here XOR, we got first of all XOR of all of them, and if we do XOR with this portion would be duplicate which already calculated, so this portion would be nullified, we will left with only this part as XOR. So that is why we are doing here, what we are doing for first part, we are doing XOR val of 0, this guy would have XOR of all the nodes, then we are doing the first cut, XOR val of u, so we will get the first portion XOR. Now similarly under this guy we have, because we have made only 2 portion and we have to make 3, right? So let's say we are making one more cut here, suppose I am making this cut here, okay. So now for this portion similarly we have to calculate, so see here, then what we are doing, to get this portion XOR val of u and XOR val of v, right? So this portion will be the XOR of this affected one, right, for this one, right, because we are doing at u we have the XOR of all these guys, right, and then we did the XOR of this guy. So then we will left with here, because the duplicate values would nullify in case of XOR. Okay, now we are going for the third part. Third part doesn't have anything, then whatever the XOR value it, that value, right? Now we have calculated, this is coming when when u is the ancestor of v, right? So I have written with get diff method, which is simply giving us the value, right? This is the get diff. We are getting the max of this all these three part and the minimum of all these three part, and their difference we are returning here, right? So same thing we are calling here. So now you guys would have been observed here that if u is the ancestor of v, we are getting the diff, whatever diff, and we are putting it into the this result value. Otherwise, if this is not the case, then v might be the parent of u, or you can say v might be the ancestor of u. In that case also we are calling in the vice versa of this if condition. If this condition is also not true for u and v, that means they would be not at all the ancestor kind of stuff, right? The graph could be also like this, right? Let's say our graph, our tree itself is like this, that there is no connection, two portion is like this. For example, if we have the tree given like this, so we can say that see, this guy is not at all the ancestor of this guy, not at all the ancestor of this guy, right? Not at all the ancestor of this guy. So in that case, all of them are free from each other, right? So this else condition would be for this scenario. So for this scenario, what we are doing, we are getting the, see, for first portion, because at XOR val 0 we got the XOR of all of value 8, and XOR u we got all the value 8. So what we are doing, this will give the first part XOR val, right? First part, let's say that graph was like this only, because at XOR 0 we have got the XOR of all of them, right? For that reason we are doing here all the three, right? And similarly here we are calling it freely XOR val u and XOR val v, because they are not connected at all, right? So this would be our third condition. So every time we are calling this get diff method, and we are parking the value into this variable res. Okay, so now if I execute this code, let me run it, which I have already submitted, but I am still doing for the sake of video, and let me submit it. So what would be the time complexity here? It is 93.10% faster. So what would be the time complexity? So see, we are calling this 2 for loop for every u and u plus 1, right? So this is basically in giving in the quadratic. So this the time complexity would be O of n square here. So so guys, and what would be the space complexity? Space complexity we are taking, see, we are creating the extra arrays of size n. So in general we can say O of n would be the space complexity. So thank you for watching this video, and if you guys have any concern, please make a comment over there. I would be definitely come back to that.